So I am pleased to introduce this next session focused on structures and materials in the department. And like a lot of our other sessions, this is dominated by faculty that have very recently joined the university. And our newest faculty member is Dr. Suhasini Guaraja. And as I mentioned, she comes to us with a lot of experience already. And so we're excited to add that to Auburn. But this is her first chance to really tell this community what she's been working on and what she will be working on at Auburn. And so with that, I'll turn it over to you. Thank you.
Thank you, Brian, for the introduction. As Brian mentioned, this is my third month at Auburn University. So here's a little bit about my background. So before I joined Auburn University, right after my PhD, I've actually worked for a few years, initially at Boeing on the 787 aircraft, and then later on in GE at GE Global Research. So the kind of work, after a few years working in the companies, I realized that I should go back to academia. So the kind of work that I have been doing over the last 10 years is essentially, inspired by the manufacturing issues that I witnessed while at Boeing and GE. And so the major thrust of all the work, the major idea behind all the work that we have been doing in my group has got to do with connecting manufacturing issues with long-term sustainability of composite structures. So what do we mean by that, right? So when you have a composite structure, or in fact any structure, any kind of engineering structure, I would say, the material is quite interesting, right? So these materials are known to be hierarchical in nature. So this is just an example of like a BD fabric, a bidirectional fabric, which is used quite extensively for making different components. So if you look at it carefully, these are essentially comprised of things called fibers, and the fibers could be carbon, glass, Kevlar, what have you. And they are sort of a collection of these fibers. They tend to make a toe. Each fiber, as you know, would be, the length scales would be in the range of somewhere around tens of microns. So as you keep going up the length scale, you would see that the complexity of the material also increases. So these fibers, a collection of them become the toes, and then the toes, a collection of those become a ply, and then the plies are sort of laid on top of each other in different configurations, and you end up getting BD fabric. And then of course you have the complexity which comes into an actual component. So when you process these materials, just because of the nature of how these materials are processed, what you end up getting is you would end up having defects along the way. So here is an example on the right of what the materials, at different length scales, how the material structure actually varies. So if you're looking at understanding how compression behavior, for example, happens in these materials, you would see at the fiber matrix length scale, you have what are called fiber misalignments, right? So instead of the individual fibers being exactly straight, what you would end up having is they would be at an angle. Which would obviously, if you look at it from a compression behavior standpoint, they would be extremely detrimental to the performance. And similarly, you could have something like fiber waviness, or if you have a more complex structure like this, suppose some sort of a curved composite like an L section, or then you would end up having what are called fiber wrinkles. So the objective of any kind of study that sort of looks at these microstructures would be to look at the correlation between the microstructure with the process, and finally the property that you would obtain for these kind of materials. So just to give an example, one of the projects that one of my PhD students is sort of finishing up is on CMC mini composites. So these are called mini composites because we make these materials using individual toes. So these toes are sort of kept in place while you have a process called chemical vapor infiltration that occurs. And you end up getting, a microstructure somewhat like this. So in addition to the constituents of carbon, boron nitride, and silicon carbide, which is a matrix. So carbon is the fiber phase, boron nitride would be the interface, and SiC would be your matrix phase. So in addition to having these three constituents in your composite, you also have a fourth phase, which is pores, which occur as a function of the process parameters that have been used. So in this work, we have sort of looked at, like 9 different configurations of boron nitride and silicon carbide, and we have sort of studied how the behavior occurs. So the other thing to also note is the performance. As I was mentioning, the performance would be, based on the microstructure, which is obviously dependent on the process. So one of the things that has not been, has not received as much attention is, say, if you want to predict what the performance of these kind of materials would be, we have, you can take that from a sort of, you could take certain configuration, like a spatial configuration of how the fibers are distributed in a matrix, and sort of analyze that structure. But what is more interesting would be to sort of figure out what your fiber, spatial orientation of fibers, spatial location and orientation of the fibers would be in relation to the process parameters, so that you can have an inverse way of changing the process parameters while you're making these materials. So have some sort of an inverse optimization method to come up with a microstructure that would be beneficial in terms of performance. So that's one aspect. The other aspect is things like fiber clustering that you see. So you would see that invariably your distribution of the fibers in the at the microstructure level is not uniform, and that has a huge effect as far as damage predictions go. So you would obviously, if you have two fibers that are close to each other, the the volume of material that is, say, in between the two fibers, so those would be the points where you would see damage initiation that would get triggered, and that would sort of grow as you go across the length scales that you have. So those are sort of some of the open questions that we are interested in understanding. The other added complexity here is, what are the constituent properties, right? So the properties of the constituents, if you do tests outside of this particular process parameter, you would get one set of results. But if you take these constituents in situ and you try to conduct tests in situ, the properties that you would get would be slightly different. So there is some amount of uncertainty in what the constituent properties themselves are. So that also has to be sort of figured in when you are looking at the performance of these kind of materials. So we have done, so that sort of brings into different kinds of tests that we have done to understand the the tensile response of these materials. So one of the reasons why you have boron nitride is as an interface is, as you can see over here, the presence of of an interface, a weak interface actually helps in improving the performance of your composite. So typically these carbon silicon carbide kind of materials are extremely brittle. So if you do not have an interface, you essentially the material just cracks very easily and shows brittle fracture. But in the presence of interface, you do have a lot of fiber matrix debonding that happens, which sort of gives you a quasi-ductile behavior when you look at the tensile behavior of these kind of materials. And we have done a detailed investigation trying to identify what the matrix crack densities are, and all of this sort of goes into in relation with the porosity that also exists in these materials. So here is an example of using something like micro CT, computed tomography, to identify the distribution of pores. As I was mentioning, this is essentially like a fourth phase in your material. So, looking at the distribution of the pores, looking at different filtering schemes to essentially identify, the important constituents, the important parameters that you would use to identify a pore, having different ways of sort of, defining what these different parameters are from the micro CT data. So that would help us to have a model of your response that takes into account the effect of porosity. So there are obviously things like the proximity of certain pores, the geometry of certain pores in relation to, say, the fiber, that has to be studied separately. But by and large, if you capture the distribution of the pores and identify the important parameters, you could essentially have a matrix phase inclusive of the process defects that you could use to identify identify and predict what the performance is going to be. And so we are sort of looking at a progressive damage modeling framework, wherein we allow for, it's like a three-phase shear lag model that we have developed. So the matrix, fiber, both of these materials are assumed to have like a viable strength distribution because they're extremely brittle materials. And the viable data is based on the testing that we have done separately. And so we allow for mechanisms such as matrix cracking to happen. We allow for fiber breaks to happen, and essentially, this three-phase shear lag model allows us to, have the matrix crack, for example, get arrested at the interface matrix region, or we can also look at what happens when the matrix crack goes all the way till the fiber phase. So that allows us to get this kind of a response. And as you keep increasing the number of, increasing the far field applied load, we see that the matrix crack density sort of increases. So here is, again, a framework that we are using to identify the progressive damage modeling for these kind of materials. So this is one example of how you would explicitly account for the process defects that occur. So in addition to that, so that was as far as CMC materials goes. So we have also done quite a bit of study to look at polymer matrix composites. So this is, for example, one of my PhD students who recently looked at how, in a liquid composite molding process. So he has developed like a finite difference based two-phase flow simulation model using a level set approach, wherein he is he looks at the pressure difference, which is essentially what's driving the resin to flow in this configuration. And the green fishnet kind of a material that you see here is essentially called the high permeability medium. So in these kind of processes, what is the typical approach is you would have a high permeability medium, sort of a layer that would be kept on top of your porous preform, and the idea is the resin would essentially flow faster in the high permeability medium and sort of seep in along the thickness direction, so that reduces the required time for fill. And what we were interested in was looking at something like this. So if you have a geometry with something like a plate with a hole, what would typically happen is if you do not have a good process modeling setup, you would end up having a region of a dry patch, for example, right after the hole is located. So typically what would be required is now have another inlet over here that would sort of, the moment the resin sort of comes to this region, this inlet opens up, and then you would be able to optimize the flow process in a more efficient way. So this is, and we've also sort of looking at how the permeability of the preform changes depending on the process parameters such as compaction, or suppose if you have like a hemispherical shell and you're draping the preform on top of it. So and if you have a BD fabric, you would end up having something like shear locking mechanisms that happen. So what would be the input? What is the input for the process modeling, the softwares that exist? What sort of inputs do you need to take as far as the permeability goes? So those kind of studies is what is of interest to us here. So in addition to that, we have done, detailed investigation of, if you look at machining, for example, you could think of it as a controlled fracture process. So how does the material actually behave when you're trying to remove some material out of it, right? So it could be drilling process, it could be something like orthogonal cutting, milling. So these processes, again, there are associated, friction that comes in. So we have measured temperature. We have tried to understand how does surface integrity change during these processes, and how that can be correlated with the structural integrity of a component. So besides that, we have also looked at micromechanics of damage for polymer matrix composites, inclusive of things like residual stresses. We have looked at, as I was mentioning, for a particular spatial distribution of fibers, what happens to the failure envelopes, correlating the microstructure with the performance. And we have also looked at classical problems such as, the multiple fiber fragmentation, how that occurs. And we have done upscaling as well. So in an actual laminate, how does, how does the, not just the strains, but also the damage modes, how they sort of evolve. So besides this, we have also done microstructural improvements. So, aligning CNTs, for example, using non-uniform electric fields to improve the, strength of these materials. These are GFRP materials, and, use of multiple electrodes to sort of span a larger area, so that this kind of a process can be used for an actual structure. So those are sort of the kind of studies that we have done. And there is a bunch of experimental mechanics based studies which looks at in situ property measurements as well, that forms the that is of interest to our group as well. So I will stop here. Thank you for your attention. If you have any questions, I would be more than happy to answer them. Thank you.
Thank you, Sudasini. I definitely enjoyed it. I learned more every time. We have time for a couple questions, if anyone's brave enough.
Well, I'm brave enough. So this is Chris Crumley. I just some of your investigations, can they be done non-destructively to understand what may already be through the supply chain, and what has been produced?
Oh, absolutely. So the micro CT work that I was depicting, those are essentially non-destructive tests that can be done to understand the microstructure. Again, in relation to the process parameters, and other investigations such as, we have also done infrared thermography to look at defects that exist in components. And of course, ultrasonics is something that can also be used. Yeah.
Okay, so if I may follow on, what I was thinking is, as you were discussing this, if we could find a way to statistically understand through a certain supplier and through a certain process or makeup or even machine dependent, can we get a statistical understanding of what type of defects were and maybe a knockdown factor on that particular structure?
Oh, absolutely. So that is essentially what I was talking about. So one is in terms of the defects themselves. The other thing is, as I was mentioning, would it be possible to have some sort of a quantification of what the how the fibers are sort of clustered together. So that would give us indication of what the property of the particular component would be. So yes, absolutely. So those kind of techniques can be used.
Very good, and thank you. Welcome to Auburn.
Thank you.
All right. Thank you again, Suhasini. I think we'll move on to our next speaker, Russell Malin.